Hi folks, we're going to take a look at some examples of graphing combinations of functions, and we'll start with number 1 from Unit 6, Lesson 4. So they give us the graph of two functions, and in fact they even give us their equations, but a lot of the things that I'm going to do here we'll be able to figure out just by looking at the graphs themselves. Okay? So in the first one, we're doing f plus g at x, which of course is just defined as f at x plus g of x. So when I'm looking for the y values of this function for a particular input, I'm just adding up the y values of the individual ones. Okay, and what I'm going to do is I'm going to follow the same procedure as I did, say, for graphing rational functions. I'm going to try to go in a particular order. So first of all is to determine what the domain is, and we see here that f, so first of all we're looking for all values that are in the domain of both. Okay, so f, which is 2 to the x, has a domain of all real numbers, so no restrictions there. And g, which is log base 2 of x squared, the only restriction it has is at x equals 0. So my domain are all x values in R except for 0. Okay, so next thing I'm going to do is I'm going to look for my x-intercepts. Okay, so when is f at x plus g of x going to be equal to 0? When they're negatives of each other. So I'm going to try to find x values where the y values are negatives of each other. So in this area here, they're both positive, so that can't happen. Both positive here. So I'm only going to look for where they're both negative. Where they're positive and negative. So here, if I look in this area here, where f is positive and g is negative, it looks like somewhere in this area, there's going to be a point where they're exactly negatives of each other. It's hard to tell exactly where it is. Since it's a graph, it's just a guess. So somewhere in there, I know I'm going to have an x-intercept. And if I look in this region here, it looks like I can find some value where they're going to be negatives of each other. Again, tough to tell exactly where it's going to happen, but I'll just pick a point that's reasonable. Okay? Now, those are the only places I'm going to have x-intercepts. So now let's look to see if there's any discontinuities. So the only places where I would expect to find a discontinuity is at 0, where one of the functions has an asymptote. Okay, so let's try to figure out what's going on at 0. So if I look to the right of 0, okay, what's going on? F is approaching 1. So say, it's like 1.1, 1.01, 1.001. And then what's happening? I'm adding to that a number that's getting extremely small, very, very negative. Okay, so I might have 1.001 minus, plus negative 100,000. So in the end, the result is I'm going to end up with a very small negative number. So it looks as though I'm still going to have a vertical asymptote at 0. Okay, and it's going to be going to negative infinity on the right. And if I look to the left, something very similar is happening because I've got f, which is a number very close to 1, and I'm adding a very, very small negative number. So I'm still going to end up with a very small negative number. So I'm still going to be going to negative infinity. Okay? And that's the only place where I expect to find a discontinuity. So now what I'm going to look at is end behavior. Now perhaps before doing end behavior, I might look for some nice points I could draw. And when I talk about nice points, I say, well, hey, here g is 0, so when I add it to f, it's going to be whatever the value of f is at that point. So there you go. I know that point's going to be on my graph. Similarly here, g is equal to 0, so 0 plus whatever f is equal to. So there's another nice point. So if you happen to find some nice ones, use them. Here you can see that at 2, they both have very nice values, 2 and 4, so 2 plus 4 is 6. Not completely necessary, but it does help you draw the graph. So let's not go to the end behavior. So as x approaches positive infinity, what's happening is I'm adding two big positive numbers, and what happens when I add two big positive numbers? I get another big positive number. So here, and this point kind of gives me a bit of a hint, is I'm taking 2 to the x, which is getting really big, and then I'm adding some positive number to it, so it should be getting bigger even faster here. So I think I have enough information to now draw the right-hand side of this graph. So from negative infinity, we know there's going to be an x-intercept somewhere around there, and then it's going to go through these points, and eventually it's going to approach positive infinity even higher than 2 to the x does. Okay? So now let's look at the end behavior on the other side. So f is this function here. So f is approaching 0, and g is approaching positive infinity. So I'm taking something close to 0 and I'm adding something large and positive to it, I'm still going to end up with something large and positive. And when we think about it, what's happening? Okay, I've got this function g and I'm adding something which is getting closer and closer to 0. So the function which I draw should start to look more and more like g of x because I'm adding something which is almost equal to 0 to it. Okay, so I think I have enough information to draw this graph. So I know this is going to be going to negative infinity on that side. And then here it's going to be going to positive infinity. And it should be getting closer and closer to g of x. So it should look something like this. Okay. Now, might there be other things going on in this graph? Might there be a squiggle here or an absolute, local max or min somewhere? Yes, but we don't quite have that information or have enough tools to really look for that. So the graph should look something like this. Okay, so let's now move on to f divided by g and see what happens there. So now I'm dividing these two. So this is defined as f at x over g at x. Okay, so the domain will be very similar to this one here, except I might have some other restrictions because I also have to restrict anywhere where g of x is equal to 0. So I know that I've got issues at 1 and negative 1. So I'm going to have to also determining what's going to happen at those discontinuities. Are they going to be asymptotes? Are they going to be holes? Okay. So domain, a little smaller than this one here. So it's all real numbers except negative 1, 0, and 1. Okay, and now let's look for the x-intercepts. So here I have a fraction. Where is a fraction equal to 0? It's 0 wherever the numerator is equal to 0. So let's take a look. What's the numerator? 2 to the x. 2 to the x is never equal to 0. So I know there can't be any x-intercepts. Okay, so let's move on now to the discontinuities. So I've got 3 to work with. So let's start with negative 1 here. So let's see what's happening. The numerator, f, looks like it's approaching 0.5. So it's approaching some number, 0.5, some positive number. And to the left of negative 1, what's happening? I'm dividing by something that's getting closer and closer to 0. And what happens when I divide, 0.49999 by 0.0000001, I'm going to end up with a number that's very large. Okay? When you divide by something very close to 0, you end up with something very large. So it looks like I'm going to have an asymptote at x equals negative 1. And here, since I'm dividing a positive number by a really small positive number, I'm going to positive infinity. Okay, and now let's see what's happening on the other side. Okay. Something very similar. The numerator is approaching 0.5 and the denominator again is approaching 0. Okay, so that's going to make my number, go to infinity. Except in this case here, I'm dividing a positive by a negative number, so it means it's going to take it to negative infinity. Okay, and I think you can see something very similar is going to happen at 1. Okay, because I got a very similar scenario. Okay. My numerator is just approaching some number. In this case here, it's approaching 2 from either the left or the right. And then I'm dividing by g, which is getting very, very close to 0. So similarly here, I'm dividing two positive numbers. So it's going to go to positive infinity. And then here, I'm dividing a positive by a negative number. So it's going to go to negative infinity. So I've covered these two discontinuities. Now let's see what happens at 0. Okay, so in the numerator, say if I look on the right, I've got some number close to 1, 1.001, and I'm dividing it by some really, really small negative number. So imagine you divide 1.001 by negative 100,000. You're going to end up with a negative number that's very, very close to 0. So I should be approaching 0 on the right, and very similarly on the left-hand side. Again, I've got just some positive number close to 1 that I'm dividing by some really, really, really small negative number. It's again approaching 0. But this function can't be defined at 0 because g has an asymptote there. So that must mean I have a hole. And then I'm going to negative infinity on one side based on what we determined earlier, and negative infinity on the other side. So I'm going to have something that looks like this with a hole at 0. Okay. All right, so let's move on. Anything else, any nice points we can determine? Well, hey, here I see that the two functions are equal. And when two equal numbers are divided, well, it's just equal to 1. So I know right around here, the function's going to be equal to 1. And let's look at the end behavior. So what's happening? I've got f, which is approaching 0, and I'm dividing that by a big positive number. Well, guess what? It's going to make it go to 0 just that much faster. So what we have here is our function must look something like this. It's going to cross there, and it's going to approach 0. Well, not drawn too nicely, but something like that. And let's see what's happening on the right-hand side. Okay, here I've got a really big number divided by another really big number. Oh, what's going to happen there? Well, here, this is exponential, and that's logarithmic. Exponential grows much, much faster. So this is a much bigger number at any value as x approaches positive infinity. So this is the one that's going to take over. So at some point, it's probably going to come back down, and it's going to have to come back up and approach positive infinity. All right? So you're going to have something that looks like that. So let's go back and see if we can find a bit of an algorithm here. And the algorithm, like I said, is very similar to what we did with rational functions. Step number 1, determine what domain you're working with. Step number 2, try to find any x-intercepts. Okay, so for an addition, it's when the y values are negatives of each other. For a division, the numerator has to be equal to 0. For a multiplication, either one of them is equal to 0. So depending on what operation you're performing. Next, analyze all discontinuities. So discontinuities might turn out to be vertical asymptotes. They might turn out to be holes. Okay. Look for any nice points that you can draw besides the x-intercepts, if there happen to be any that you notice. Okay. And lastly, determine the end behavior of the functions based on the behavior of the individual functions. And then from there, you should have enough information to sketch the graph. Okay, so we'll stop this one here, and I'll make another video for number 2.